Okay, welcome to my first kidney video essay here. So let's just jump right in. So we're starting out with filtration and reabsorption here. So you have a structure in the kidney called Bowman's capsule and the glomerulus, which is a capillary. Together they construct the renal corpuscle. So inside the glomerulus, it's a fenestrated capillary, which means that it has these holes in the capillary membrane that allow things to diffuse out. It also has a basement membrane that is negatively charged, so it'll repel negatively charged particles. Not all of them though. And then we have our podocytes that are they have these little finger-like slits that are gonna help with filtration. And then we have mesangial cells as well. So basically, what happens here is these holes are very small, so things like little molecules of glucose, hydrogen, sodium, bicarb are gonna come out of these holes. But the things like red blood cells, those things aren't gonna fit through these holes. They're too big. So in the glomerulus, we have an afferent and an efferent arteriole. And we can control the blood flow rate that goes into this capillary, and that will allow us to control the GFR. One way we can do that is to constrict the efferent arteriole using angiotensin II. So what that will do is that will raise the pressure in the glomerulus by causing a backup of blood in there because of that constriction. And in the glomerulus, we have a capillary hydrostatic pressure of 55, which can be influenced by our blood pressure. We have a pressure of 45 coming in, which is made up of our B cup, and then our hydrostatic pressure of Bowman's capsule. So this results in an overall pressure of 10 going out of the glomerulus. And then we can also, there are these special cells called macula densa cells. And what these will do is if they sense low Na concentrations or like low blood pressure, they're gonna go ahead and stimulate nitric oxide, which is gonna dilate the afferent arteriole, cause an increase of blood flow to the glomerulus, and then it's gonna raise our hydrostatic pressure and therefore our glomerular filtration rate, because our GFR is directly related to how much blood pressure we have going through that capillary, because that's the force that is driving the filtrate out of the capillary there. We also have our myogenic response. So in response to blood pressure, there are calcium channels on the afferent arteriole, and when they get stretched by high blood pressure, they release calcium, and then that's going to cause a contraction. That's going to cause that afferent arteriole to constrict a little bit. Our tubuloglomerular feedback is that release of nitric oxide. It can also release adenosine to constrict that arteriole if the blood pressure is too high as well there. Okay, so that is basically filtration for you, and then how we can control the blood flow into the glomerulus. So now let's go over tubular reabsorption. So not everything that leaves the glomerulus is, we don't want it all to get peed out. We want the bad stuff to be filtered out of the glomerulus, but we want to reabsorb the good stuff like glucose, sodium, bicarb. What else we got? Amino acids, calcium. We want to reabsorb those things. So we have this structure called the proximal tubule, which is where a lot of this reabsorption happens. And it happens using the sodium gradient caused by the sodium-potassium pump. That's very important there. So what's going to happen is those sodium-potassium pumps are pumping sodium out of the cell and potassium into the cell. This causes a gradient for sodium to want to enter into the cell. So we're going to use the energy that is found in this gradient to perform secondary active transport. And we can do this to move things like glucose, amino acids, lactate, and then bicarbonate into the cell. Because as that Na wants to enter into the cell, we can use that energy to do things like move hydrogen ions out. We can move glucose in with that Na flow. We can move amino acids in with that Na flow. But it's very important to know that that energy that is driving that transportation is secondary active transport. That energy is contained in the gradient, the chemical gradient of sodium that is caused by the sodium-potassium pump. So now with bicarb, it's a little interesting here. We can have CO2 come into the cell from the bloodstream, react with H2O, which is going to form our carbonic acid, which dissociates into a hydronium ion, and then our bicarbonate. And then what we're going to do is we're going to use an antiporter, which is going to pump sodium into the cell and then hydrogen out. The bicarb that we produce is going to go back into the bloodstream. And then that H plus ion is going to go out and is going to bind with another bicarb, which is going to turn into H2 and CO2. H2O and CO2. And we're going to go ahead and excrete that out of the cell there. And then additionally, we have a concept called solvent drag, right? So all this sodium reabsorption is going to cause an osmotic gradient that water wants to follow. So as we're moving this sodium into the interstitium and back into the bloodstream, water wants to follow the sodium. It is obliged to follow that sodium. And so in the proximal convoluted tubule, we're going to reabsorb 70% of the filtered sodium, and we're also going to reabsorb 70% of the filtered water, 1:1 TFP ratio. And we're going to absorb 100% of the glucose. Because if you have any glucose that's being excreted out in the urine, that is very inefficient. Why would we want to pee out our body's main source of fuel, right? So we need to reabsorb that. But there's a concept called saturation, where if we have too high of a amount of glucose that is being filtered out, if we have too much glucose in the blood, what that's going to do is it's going to saturate the sodium and glucose transporters, right? Those transporters can only transport so much glucose at a time. And if we have too much glucose in the tubules, not all of it's going to get picked up and we're going to start peeing it out. And then additionally, we have a concept called renal threshold, which is basically like the maximum amount of a substance that the tubules can reabsorb at a time. And for glucose, that's around like 180 to 200 milligrams per deciliter. So any more glucose in the blood than that, and we're going to start excreting it in the urine because our transporters are not able to pump it all back into the cell. And we got this concept called solvent drag here, which is where as water is following the sodium, it's going to bring with it calcium and potassium, and that is our paracellular transport of reabsorption. And then using the channels is, of course, transcellular transport. And then as all those ions are entered into the cell, they're basically going to get put out back into the bloodstream via the sodium-potassium pump or other like leak channels that they can use there. So chloride is reabsorbed through antiport with bicarb. And then amino acids are reabsorbed through symport with sodium. Most of these are reabsorbed through symport with sodium there. That's why we have so much sodium and water being reabsorbed here in this part of the tubule. So now we have a concept called clearance. Clearance is the rate at which a substance is filtered from the plasma compared to the rate it is excreted in urine. Our concentration for this, or our equation for this, is our clearance rate equals our urine rate times urine volume over our plasma concentration of the solute. So clearance can also tell us the glomerular filtration rate. Because if we find a substance there's a few criteria we need. It has to be freely filtered from the glomerulus and not reabsorbed, and also like small and non-charged. So a substance that matches these criteria is called creatinine. It's a metabolic byproduct of creatine phosphate. So creatinine is freely filtered in the glomerulus, it's not reabsorbed in the tubules. And so by measuring how much of that is cleared into the urine so we can measure the amount of that in the plasma and then the amount in the urine. And we can compare those to find out our GFR, because it's an accurate representation of how much the glomerulus is filtering, since it doesn't get reabsorbed at all. So that can tell us our glomerular filtration rate there. Yeah, so now moving on to our renin-aldosterone-angiotensin system. This is how basically we can control sodium and water reabsorption to increase or decrease blood pressure and we can regulate plasma osmolality and the extracellular fluid amounts here. So first we have the liver, which is going to produce angiotensinogen. We have the kidney, which is going to sense low blood pressure most of the time and release renin. Renin is an enzyme that cleaves angiotensinogen into angiotensin 1. And that's going to be in the bloodstream there. It's going to travel to the lungs, where we have an enzyme called ACE2. And ACE2, which stands for angiotensin converting enzyme, is going to convert angiotensin 1 into angiotensin 2, which for our purposes is going to stimulate the posterior pituitary gland to release antidiuretic hormone. And it's going to stimulate the renal medulla to produce aldosterone. So the cellular effects of those. So for ADH, in our apical cells of the end of the tubules, kind of collecting duct, distal convoluted tubule area, we are going to have ADH act on this cell, and that's going to cause vesicles full of aquaporins to be implanted in the membrane, and that's going to cause the reabsorption of water here. So this is going to increase the concentration of our urine since we're taking water out. It's also going to increase our blood pressure because we're increasing our blood volume by adding more water into the bloodstream. I'm getting really thirsty for water, that's funny. And then we have aldosterone, which is going to increase the activity of and the expression of the sodium-potassium pump. So that is going to move more sodium into the extracellular fluid and into the blood. So, and then naturally water will follow, right? So what that is going to do is decrease the concentration of our urine, or it might keep it the same if water moves. And then we have our loop of Henle and our ascending and descending tubules. And so this creates something that is known as let me look this up real quick. What is that called? I'm choking. One second. Oh my goodness. Man, I cannot find this in the textbook. Pretty bad. The countercurrent multiplier system. Goodness, it took me like 2 minutes to find. So right here in the loop of Henle, we have our countercurrent multiplier system. So it's important to know that our capillaries, our peritubular capillaries, run this way, and our peritubular capillaries run this way. So what's happening here is as we go down the descending loop of Henle, we're releasing H2O into the blood. So if we're decreasing water in the blood, that's going to increase our concentration of ions in this gradient here. And then on the other side, on the ascending, we're going to reabsorb all of those ions into the blood. And so this is going to dilute our tubule, and our osmolarity is going to move back up. So it's important to know that our capillary is running the opposite way that I just described. So as the capillary runs over this, first it's going to pick up all of these ions, and we have these channels that are pumping sodium, chlorine, or chloride, potassium back into the blood. And then what's going to happen is that's going to make it so that there's even more of a gradient for water as it's leaving through the descending loop of Henle to want to go back into the bloodstream. So this just amplifies our ion and water reabsorption, right? Because if those capillaries were going the other way and we're reabsorbing water first and then ions second, it just wouldn't be super efficient, right? And then the vasa recta goes through here on the juxtamedullary nephrons, right? And then we also have urea in here, which is going to add to the concentration gradient there. So yeah, so that is pretty much this first unit here. Let me see if I missed anything that I need to go over. Sweet. Yeah. Yeah, so basically the more ADH we have, the more concentrated our urine is going to be, because we're going to be absorbing that water. And then in here, the more ions we have coming in, the more water that we're going to want to come into our bloodstream. And so if we're absorbing water, that's gonna make our urine more concentrated as well. All right, so that's the video. Thanks for watching.